Okay, so we're going to be looking at solving the differential equation dy by dx is equal to 2 times x times y times the exponential of x over y squared, all divided by y squared plus y squared times the exponential of x over y squared plus 2x squared times the exponential of x over y all squared, subject to initial data that when x is 0, y takes a value of 4. Now, this is a homogeneous differential equation. So the standard approach is to introduce the variable z to be y divided by x. And our goal is to express our differential equation in terms of x and z and not in terms of y. So this means that y has got to be equal to x times z. And so dy by dx is the same as d by dx of x times z. In other words, we're differentiating a product here, we have to use the product rule. So the derivative of x times z with respect to x is going to be x times dz by dx plus z. So let's substitute this into our differential equation, noting as well that on the right hand side the x divided by y all squared term is nothing more than z raised to the power of minus 2. So making these substitutions, we see that z plus x times dz by dx is equal to 2x squared times z e to the z to the power of minus 2 all over x squared z squared plus x squared z squared e to the power of z to the power minus 2 plus 2x squared times e to the z to the minus 2. Now if you notice here we've got an x squared featuring on all the terms on the top and all the terms on the bottom of this right hand side, so they will cancel. Now let's take a look at what we've got. So z plus x dz by dx is equal to that horrible fraction on the right hand side. Let's rearrange this to get all the z's on to the right hand side. So we take z away from both sides, and if we now write the right hand side as a single fraction over a common denominator, if we do this, we notice that there are some terms on the top that cancel, shown here with the red and the blue circles. So these terms cancel, and we now rearrange by separating variables. So we end up with a z squared, 1 plus e to the power of z to the minus 2 plus 2e to the z to the minus 2 all over z cubed, 1 plus e to the z to the power minus 2 dz on the left hand side, and minus 1 over x dx on the right hand side. We're now going to split up this left hand side and integrate both sides. So on the left hand side we've got z squared plus 1 plus e to the z to the minus 2 all over z cubed, 1 plus e to the z to the minus 2. Well, that cancels to 1 over z. Our second term on the left hand side, well, that's 2 times e to the z to the minus 2 all over z cubed plus, z cubed times 1 plus e to the z to the minus 2. Our right hand side is just the integral of minus 1 over x. Now, the first and the last of these integrals is obviously quite easy to work out. It's the one in the middle that might cause us some problems. So to determine this integral in the middle, let's think about what methods we can use to do this. First of all, can we integrate this directly? The answer, of course, is no. Our goal then is to think, can we use a substitution? In other words, is there a function here and its derivative? If we look at the term in the bracket, the 1 plus e to the power of z to the minus 2, if you differentiate that, you have to use the chain rule. And the derivative of that term in brackets is the derivative of z to the minus 2 multiplied by the exponential of z to the minus 2. Well, the derivative of z to the minus 2 is minus 2z to the minus 3, and we see that that term features in our integral. So it means that that substitution is a good choice. So let's introduce a u to be 1 plus e to the power of z to the power of minus 2. So that means du by dz is minus 2 times z to the power minus 3 e to the z to the minus 2. That's using the chain rule. And if we rearrange this fraction, we see that minus du is the same as 2 times e to the z to the minus 2 over z cubed multiplied by dz. In other words, that integral we're trying to work out is nothing more than the integral of minus 1 over u with respect to u, and of course the integral of that is the natural logarithm of u. So, going back to our previous slide where we had those three integrals, we know that first integral 1 over z is natural logarithm of z. The middle integral we've just worked out. It's minus the natural logarithm of 1 plus e to the z to the minus 2. And the integral on the right hand side must be minus the natural logarithm of x. And let's of course add on a c here being the constant of integration. Now by using the laws of logarithms, minus log x is the same as log x to the minus 1, and the same thing is true for log of 1 plus e to the z to the minus 2. Now if we take exponentials of this term here, we end up with z times 1 plus e to the z to the minus 2 to the power of minus 1 is equal to a times x to the minus 1, where a is a constant. So recall that trick, the exponential, if we look at the right hand side, the exponential of log to the x minus 1 plus c is the same as the exponential of log to the x minus 1 multiplied by the exponential of c. This exponential of c is just a constant because c is a constant, so let's call this exponential of c to be the value of a. Right, so now let's try and simplify this term a little bit, this solution if you like. Well, if we take our term in brackets from the left hand side up onto the right hand side, we see that z is a times 1 plus e to the z to the minus 2 all over x, and if we now remember that z is nothing more than y over x, let's substitute in for z, so we see that y over x is equal to a times 1 plus e to the x over y all squared all over x. Well, the x's here cancel, and we get that y is equal to a times 1 plus e to the x over y squared. This is our general solution to the original homogeneous equation we were trying to solve. Now let's recall we had some initial data, specifically that y took a value 4 when x took a value 0. So if we substitute in for x is 0 and y is equal to 4 into our general solution, we see we get 4 is equal to a times 1 plus 1. Because the exponential of x over y squared is the same as the exponential of 0, the exponential of 0 being a value 1. So this tells us that our constant a has got to be equal to 2. So let's substitute in a equals 2 into our general solution, so we get that y equals 2 times 1 plus e to the x over y squared. That gives us our particular solution to the homogeneous equation.